only catch is that I may get frozen due to low or competing resources in our internet at home. So please let me know if I get frozen, and I will pause. And I may have to cut video if the bandwidth is not going to support it, but we're going to do the best that we can. All right. So one thing that I forgot to mention last week, hello everybody, happy Thursday, welcome back, all that stuff, is that I had a few discussions with folks about the last question on homework 1. It was about how many and what kind of parameters are in a heterogeneous Toeplitz model. And I realized after answering the question that the way that I had worded something on the relevant slides was inconsistent and potentially confusing. I had put in the Toeplitz correlation into the R matrix as it should be, but then in the heading that describes the model, the word said covariance. So what they should have said is correlation to be consistent. So what I'm going to do is just throw out that question. So I will just take whatever answer and just take that question out of the total, and so you'll end up getting whatever credit you have for the remaining questions. I have not done that yet because there are a couple people that I'm waiting on to finish homework 1, and I don't want to have to redo this multiple times. So I'm waiting for everyone to get it done, and I will fix that one question and update the grades accordingly. You should have, let's see, homework, where are we at here? We just did formative assessment, and that means homework 2 is out. Does that sound right? Trying to keep myself organized here. I got one email from Mavis. I haven't had a chance to do your troubleshooting, but other folks, if you're running into problems, please either send me a screenshot of like your code and what you're trying, or send me, your spreadsheet or whatever you're using to answer the questions, and I will try to help you figure out where things are going awry. Otherwise, I put up, so we have new stuff for today. We have lecture 6 and example 6a. So this is a very long unit, relatively speaking. There's actually 4 different handouts that go with this unit in terms of different types of nonlinear models. And I even decided to add one more type, which is an SEM variant. But not all packages can do all the different types. So the ones that all 3 of the packages that we're using can do, which is the polynomial models and the piecewise models, and log time is the very last one. I'll go over all of those. Anything that is either SEM specific or program specific, like the truly exponential models, I will make a video for instead, because that way you don't have to follow along if it's not something that you can readily adapt to your research. I haven't made the videos that I promised yet for the SEM versions of the growth models, but I will be doing that over the weekend. That way you can have those to watch next week when I'm out of town. So I haven't forgotten. It's just that I got to get the handouts ready for each day, and it's that point in the semester where I'm just barely hanging on in terms of the pace of things. So I'm sure you all can relate, right? Anyone else feel like you're like there's a train and you're just hanging on to the end of the train and trying not to get run over? Yes, yeah, it's that point, right, where you're hanging on, and I don't know, like a treadmill maybe is the right analogy. Like it's going and you're trying to keep up, and if you misstep, you feel like you're going to land on your face. I think that's a better analogy, but. Anywho, so any questions about logistics, homework, stuff like that you want to talk about? Getting run over by a bus, I like that one as well. Watch in the chat window, or you can talk to me. I've got my headphones on today so that I can hear you better than the last time. No? All right, can someone talk real quick so I can make sure that the audio is being picked up by the recorder? Thank you. Perfect. Yep, it went green. That's all I needed. Perfect. Okay, then let me get the screen share going, and we'll dive into lecture 6, do a few slides in there, and then we'll switch. So this will be one of those where I go back and forth between the examples and the slides. That way we can talk about the idea and then show what it would look like in terms of the code and execution. So let me get the controls out of the way. Can everyone see my slides here? Are we good to go? Not yet? Okay.
Not yet.
Not yet. I must have hit the wrong button. Un momento. Trying again.
Yeah, now I can see them.
Okay, now we're good? At least Vladimir can? There's something with the Zoom where only one person can see the screen share. Are we good? We're good. Okay, there's some more thumbs. Thank you.
Sorry, I have a question
Yeah, hit me.
prior to this new content.
Mhm.
Can you repeat, please, what's the interpretation of the reliability indices that we can calculate for random effects, please?
Yes, so they're basically any coefficient in a growth model that has both a fixed part and a random part, then you can potentially compute effect size. So either via the confidence intervals or the reliability. The intercept reliability has a relatively well established place in the literature, and the intercept reliability is also known as ICC2. It is one of the things that gets spit out by certain multi level programs, such as the HLM program. And I want to say maybe, I want to make it up. There's others that may give that one too. The interpretation is the reliability of the person, or the level 2 means. So it's person means in this context. In the context of persons within groups, it would be the group mean. So it's a question of like how reliable is that summary of the group, and oftentimes that's something that people want to know if they're thinking of that as a variable that is then to be predicted. Like in the same way that we would compute measures of reliability for sum scores or for latent variables, this is the same type of idea. Analogously, the reliability for the random slope, you can think of the same way. It's like of the variance that's over time, which is slope and also error, like how much of it is because of slope differences as opposed to the error around the line. So it's analogous to reliability in the sense that it's true over true plus error, but it's not the same in the sense that slope reliability could be low because people just don't differ from each other that much. So it's not like you did something wrong or it's a bad measure. It could just be that there's not a lot of systematic change, but there's a lot of fluctuation. So it's just a way of trying to operationalize how big a variance component is that the random effects would imply. And it's also can be used to reverse engineer what the slope variance could be in a simulation to conduct a power analysis. That's where I use it. So if you have an ICC, and if you can anticipate a degree of slope reliability, then you can work backwards using those formulas to figure out what the slope variance and what the intercept variance would have to be as population values for a simulation to do power analysis. So that's what I use them for.
Thank you.
Yeah. Does that help answer?
Yes.
Okay.
Yes, that's perfect. Thank you.
Cool. Anyone else want to ask questions before we jump into new stuff? Happy to answer questions at any point. Okay. If not, let me know if that changes. So we're going to talk about within person change over time. So building on the idea of fixed plus random effects as a way to describe individual trajectories of change. The question is, what else is there besides linear? Because linear change is probably not going to be sufficient to the extent that you have a lot of occasions or you're tracking a process in which change slows down or speeds up. So I want to give you essentially a set of menu options for what is out there. This is by no means exhaustive, but I've tried to hit sort of the larger categories, and you can search with these terms in mind for more specific options if these don't exactly fit the bill, and I can also help point you towards other category choices as well. So as usual, we have the big picture, and then we have particular variants of that, and then I have a corresponding example for each of those variants. Okie dokie. So here's some data. These are the data that are featured in Chapter 6 of the book, which is all of these examples follow quite directly. So it is the same data set, so that means you can play along at home with the data that are now available on the website, by the way. This morning I did load the example 6 zip folder that has all of the original data, syntax, and output in what are 4 different programs, including M+ for one of them. These are real data. And the story behind these data, they were the same data that we used in example 3b. It's 6 occasions where the outcome is a measure of response time to a speeded task. So the y-axis here is response time in milliseconds. And that actually turns out to cause some of estimation problems down the road because of the scale of this variable. The 6 sessions are Over a period of 2 weeks, the sample is a set of 101 older adults. So the object of this study was to examine the extent to which people show improvement in this speeded task, as evidenced by response times that decline across the 6 sessions, as well as the extent of individual differences. So what we're tracking here in terms of the metric of time is how many times they've done this task, not necessarily how far apart in time the practice sessions were, because we don't think that should matter as much as the opportunity to do this task. So these are the individual trajectories, and most people look like they improve at least to some point. There's a few exceptions to that, but these are the data. And unlike a lot of the data in my book and popular textbooks, these are real data. So that means that there may be a population generating mechanism out there, but I don't know what it is. So we're going to go through the process that you would go through as an analyst when you don't know what the right answer is, and try out different possibilities. And because of the design and because of the ambiguity as to what type of change this could possibly be, I think it lends itself nicely to trying a few different things out. So big picture first then, what are we trying to do in terms of building our model for change and what goes into each side? So first, the red side, the model for the means where the fixed effects go. The role of the fixed effects, which are estimated constants that everybody shares, is to describe the average trajectory. So if you were to estimate what the mean is at each distinct occasion and draw a line through it, what is the shape of that line? That's what the fixed effects are trying to recover. One of the things that we are presupposing in figuring out what the mean is at each occasion is what should time be? What is the theoretical process that's responsible for this change? So in the context of this study, it's exposure to the test. So have you done this 1 time? Have you done this 2 times? Have you done this 3 times? It's not how old you are. It's not what day it is. It's not where you are in a progression of some kind of, disease or development or maturation. It's exposure to the test. So in all of the examples that I have, the metric of time that I tend to use is time in study, where 0 is the first time you do it, and then I keep track of how long it's been since that time. You can never be wrong if you do it that way, because within person information then is all that time is representing. If you try to use age as time or grade as time or time since an event as time, something like that, then there's a chance that people differ from each other in where that 0 point would be. And so then you're introducing cross-sectional time variation in addition to longitudinal time variation. And that's where things get very tricky. So I tend to avoid that, the potential for misspecification that's inherent whenever you have both cross-sectional time and longitudinal time, and I just focus on the longitudinal part. And so then any between person differences, the age when you started the study, the grade when you started the study, how long you've been in whatever condition since you started the study, all of those things become person level 2 predictors then that can predict why the growth curve differs across people, but they don't help form the growth curve in the same sense as time does. So you'll hear me say time where it's just how long you've been in the study, but just know that this is something that you'll have to think about in advance. And this is the topic of chapter 10 in the book as well. Something we won't get a chance to get to this semester. So then, after we've settled on a time metric, we want to think about the design of the study and the theory of the process that is creating change. And so we know, for instance, with learning, a lot of literature can tell us what learning looks like. Learning happens non-linearly. Learning usually happens fastest at the beginning, and then it sort of levels off eventually. And that could be because of ceiling effects in the measures, or it could just be because people don't keep getting better and better at the same rate forever and ever again. So you want to keep in mind, what is the process that you're modeling, and have that inform what your structure of your model should look like. Likewise, if you have some kind of intervention design, where you have a baseline period where nothing is happening and you're just measuring them, and then you start something and you measure them after the start of that new treatment, activity, whatever you're doing, that lends itself to discontinuous change, or what I refer to as piecewise models. I make this picture here with my fingers, or linear splines is a synonym as well. And those piecewise models would literally break your trajectory into pieces. So you'd have a before period and an after period, and you can test whether there's changes in the intercepts or the slopes or various other types of things before versus after. So that can be a very powerful way to describe the effect of an intervention, especially if you have a baseline period after it where, you can talk about, does the treatment effect get maintained, as, does the slope stay the same, or does it drop off, does it go up? And so the idea discontinuous maps itself onto designs where there are phases of what happens over time, and it's not just one continuous thing. So point of the story, there's not always a ready right answer. It's a question of what do the data look like, but also what is the point of the study, and how do we make sure that we are obeying the logic of the design and the point of the study in as terms of this process. So does that make sense? Folks with me so far? A few thumbs. So I got no cameras now, so all I got are thumbs. Thank you. I appreciate the thumbing. Is that a word? It probably has another meaning that I shouldn't say, but I'll say thank you for the thumbing. And do please let me know if you if I get frozen, or otherwise if I'm talking too fast. All right, so big picture then in terms of what our choices are. You've seen this slide before. Potential models for the means range from empty, meaning time is not a part of the model for the means, all you have is a fixed intercept, versus saturated means, in which you have as many fixed effects as you have occasions. Usually you would set up one occasion as the reference, and then you would have dummy codes for the difference to each other subsequent occasion. And that's only possible to do in balanced data, or if you're willing to pretend you have balanced data. But that does give you the answer key in those cases for what the trajectory is ultimately trying to fit. What are the means that we're trying to draw these lines through? So then our job is to figure out what is the in-between option that we can use to summarize or recreate those means, that hopefully is simpler and allows us to answer questions about changed trajectories as opposed to just pairwise mean differences between adjacent occasions or something like that. So we're playing the game, name that trajectory. So in terms of baseline models for the example data that we'll be playing with here across our 6 sessions of measurement, I have the empty model in the red dashed line here. So if I fit an empty means model to these data, the prediction from that empty model is right here. It says there is no change, that the mean should be around 1770 milliseconds at each occasion. The other baseline model, the best fitting answer key, saturated means, or what people would call repeated measures Anova, treats time as a discrete variable instead. And so it takes 1 intercept and 5 slopes to make that, and the trajectory that's created by that is right here. So this line here, does this line look linear to y'all? What do you think?
Linear-ish.
Linear-ish? Yeah, I would go with that. Not really. It's kind of like, well, like this part, like they're clearly improving a lot between sessions 1 and 2, which is what you would expect, right? Like the first time you do this task, you're bad at it, and then the second time goes much better. But then from there, it kind of levels off a little. But then maybe there's like a weirdness at the end where they suddenly get a little bit better, more better than it would be expected. So there's definitely some bendiness here, but it's not really textbook bendy in terms of fitting any particular thing. But the fact that it's bendy at all is going to point me towards the need for something more than just a linear, fixed linear time slope and random linear time slope. So yeah, I'll take not really or ish as an answer to this, because again, I didn't make up these data. I don't know what the right answer is. On the variance side then, same idea. We're trying to figure out which of those fixed effects that describe the average trajectory then need individual differences. So we usually assume without testing that we at least need a random intercept. People at least differ from each other in their means over time. The question is, what else do they differ from each other in? So if we have multiple fixed effects that are defining these average trajectories, each fixed effect can potentially have a random slope that goes with it if you have enough data. So as we introduce these choices, I'll describe what the data limits are in terms of the number of slopes you can have versus the number of occasions that you can have. So we are answering the question substantively, the extent to which we have individual differences, and that's usually a question. Like, do we have variation and change, which is a logical precursor to trying to find variables that predict those differences and change. But statistically, behind the scenes, what random slopes for change are also doing is introducing heterogeneity of variance over time, as well as heterogeneity of covariance. So when we have a random intercept, that introduces one specific kind of person dependency that says that all of the occasions are equally correlated, and part of the reason for the total variation is because of individual differences in the mean. But it doesn't predict any heterogeneity of that dependency. It doesn't predict different variances and different covariances. That's what random slopes do. They then allow the variance to change over time, they allow the covariance to change over time, and each of them has a particular pattern that it then predicts as what should happen according to the model. And the extent to which those patterns predicted by the model for the variance match what's in the original data as given by the unstructured matrix, that's an empirical question. So one of the things that we'll be doing in this unit is testing the absolute fit of these models, not just relative fit in terms of what we can add to make it better, but whether we're at a point where it's good enough, whether our fixed slopes have recreated the saturated means, and whether our random intercepts and slopes have recreated the unstructured variances and covariances. And I'm saying that as two separate things because as long as we're using REML estimation, they are two separate things, because we can't do likelihood ratio tests for models that differ in their means. So we will do a different process for figuring out if the fixed effects in the model for the means adequately recreate the saturated means than we will do to figure out if the random effects in the model for the variance adequately recreate the unstructured variances and covariances. So two different things. All right, so same idea. Compound symmetry with the random intercept only is probably the simplest baseline we would entertain for longitudinal data. Unstructured is the most complex, where everything gets to be what it wants. That's only possible to do if you have balanced data and enough people relative to the number of occasions. So we're looking for something in between. So adding to our toolbox of alternative covariance structures as one set of choices, random linear time slopes as another set of choices, now we're adding in random nonlinear time slopes as a third set of choices. So in terms of the baseline models for our example data, I can do the same thing. If I only have a random intercept, so this line in particular comes from an empty means random intercept model as a starting point for the simplest thing we would do. That model predicts constant variance over time. So the y-axis on this picture is variance in response time as the outcome, and this is what the variance is predicted to be if we only had a random intercept in the model beyond our usual residual variance at level 1. And the right answer, given to us by unstructured, where all the variances and covariances get to be what they want, is the black line here. So does this black line look like the variances are changing over time? See, I'm throwing softballs here. Do the variances look like they're different over time? Yeah, I think so. Like different randomly, or different in a pattern. Pattern, yeah, they're decreasing. So that cues me in right away. Whenever you see variances that change like monotonically like this, like they're either increasing over time or decreasing over time, or they decrease to a point and then they come back again, like that sort of U-shaped trend, that is a clue that you have some kind of random slope for time that's going to be needed in your model. If the variance stayed the same over time, that's indicative that a random intercept is probably going to be sufficient. So these are, diagnostics that you can use to try and help you sort of narrow down what the possibilities are. But these ultimately become empirical questions because you can always try something and see if it makes the model better via a significance test of some kind, either a Wald test if it's a fixed effect or a likelihood ratio test if it is a random slope variance. But this kind of thing helps you at least get a start in terms of what you would want to do for a data analysis plan. So summarizing, model for the means, fixed effects related to time. That is to summarize the average trajectory. And our goal is to spend fewer than all possible parameters to do so. Likewise, model for the variance, our job is to figure out which aspects of the trajectory need individual differences and simultaneously come up with a more plausible recreation of what the variance covariance pattern is over time. Okay, I'm going to skip this slide for right now. I want to go to the example. Are we cool with that? That's sort of a rhetorical question, but yeah, we're cool with that. Because it won't make sense yet. So what I'd like to do first is go through the models that you already know on this new data set. So we went through example 5, building up from empty means up through random linear time slope. I want to do that part of this handout again as a review before we jump into the nonlinear parts via polynomials. So this is example 6a. This is a handout that I posted yesterday, and the electronic materials that go with it are now available. So this is A out of A, B, C, D for possibilities for this model. The data setup for these is a little bit more involved than usual because of the need to potentially test absolute fit. One thing that I will mention that is going to differ in this code versus what's in the book. So I tried to be consistent in the way that I named all of my predictors in the book, where if it was a centered variable, I had the centering constant at the end. So like if I had age and I centered it at age 30, then I'd name that new variable age 30, like as one unit. And I tried to do that for time, but I realized that it actually becomes confusing because if I center time such that session 1, which is the first occasion, I want to be my time 0, then I would have to name that time 1. But then time 1 makes it sound like I'm only referring to the first occasion as opposed to a variable that's centered at 1. So I decided just to drop that, and when I revised the book, which I've ostensibly been doing for 4 years now, I signed a contract in like 2018 to revise my textbook, and I'm making great progress on it clearly. I will take out time 1 and just substitute it with time because it's cleaner and that's what everyone else uses. So in this example, session is the original variable that is 1, 2, 3, 4, 5, 6. So it's a generic index level 1 ID variable like wave or occasion or something like that. Time is the centered version, which is session -1. So time is going to run 0 to 5 instead of 1 to 6. The rest of these, this is the SAS code here to make this, these are dummy codes for which session is which. They are going to be used to compare the fit of our fixed effects model back to the saturated means, and I will describe what they are for when we get to that point. But the way that I build my example files is I tend to do all of my variable manipulation, creation of predictors, all that stuff in one fell swoop. That way the data set's ready to go. So this stuff is here for now, but we're not going to need it just yet. Relevant Stata code is also right here. In Stata, I have generated my time variable, but I also had to make a squared version for use in the random effects part of the model. It would not let me do the squaring on the fly version, so I did have to compute that. Here are the same dummy codes whose purpose will be shown later. And then last but not least, in R, I have the usual process here of reading in the data file that was in the original SAS format. sorting it, I had to make a new variable called session6, whose reference was the last occasion to match the saturated means output from SAS, but otherwise this looks the same as what we had in the other packages. And then making the demicodes down here using the which function. All right, any questions on the syntax to set this up? The data are already stacked, so I didn't have to do that part. Or coding time. Anything on that? Are we good with that?
No.
No questions? Or no, we're not good? Are we good? Let me phrase it that way.
Lisa, I don't know if this was just a me thing, but everything froze for like probably like 30 seconds.
Yep, you're not just you. It's saying that I'm frozen. Okay. Let me kill my camera for a minute and see if it comes back. Okay, can you all hear me again?
Yes.
Okay. Can you live without my gestures for a few minutes? All right, are we good?
Yes.
Yes, we're good. All right, excellent. Thank you for letting me know. I don't want to just talk into the abyss if it's not going to work. If the internet at the house does not prove sufficient to do this, then I may end up Zooming from my office if the classroom is still broken. So I will, we will make it work one way or the other. I appreciate your flexibility. Okay, so no questions on the setup then. That was where we left off. Okay, I'll interpret silence as no questions. So on page 2 then, the answer key model. So I'm estimating a saturated means unstructured variance model because that is ultimately the pattern I'm trying to recreate with my model that includes slopes for time in it. So I want to know where the end goal is. I want to know what the means are, that's saturated means from the fixed effects, and I want to know what the data created variances and covariances are. So you've seen this several times. In terms of the specification, I'm using session as my variable that goes into the fixed effects because it's being treated as a discrete categorical variable by being included on the class statement in SAS. I have no random effects in the model, only an R matrix that's unstructured. So I have I.session in Stata to do that, to make it categorical. And in R, we're using the GLS function because that's the only one I could find that allows an unstructured R matrix without random effects. And I'm denoting session 6 as a factor variable. That way the reference will be the last occasion to match the other packages. So all of this stuff you have seen before, but it's all repeated here so that you can see all of the pieces of the code that I use to generate the corresponding output. So here's the story then. Our R matrix in this case, so I want to make a note here as I have over in the little box. R is V in this model. So if we don't have any random effect variances and covariances in the G matrix, then R and V are the same thing. So this is the marginal data implied, like from the data, variance covariance matrix. This would match what you get out of descriptive statistics if you have complete data. It will not match if you do not, because the assumptions are missing at random rather than completely at random if you're using maximum likelihood estimation. Okay, are we good still? Or am I frozen?
Yeah, I have a good question, Lisa.
Great, that means I'm not frozen.
Great. Yeah, in this case, do we need balance data for time?
Mm-hmm.
Equally spaced time?
You need balanced, but it doesn't have to be equally spaced.
Great. Okay, thank you.
Yes, you need balanced data for this model, and you need to have enough people relative to the number of occasions.
How much is that?
I can't tell you. At a minimum, more people than you have elements in the covariance matrix, but like that may not be sufficient. The best way to find out is to try it and see if it throws up at you. That would be my advice. Yeah. Yeah, throws up at you means non-convergence, by the way. So these are the variances that made the black line in the picture that looks like they were declining over time, and the correlations are down here. So in terms of the size of these correlations, these are pretty large. So even the correlation between the first occasion, session 1, and the last occasion, session 6, that correlation is still 0.8. Like the smallest correlation in this whole table is 7.6. So there's a very strong between-person dependency that's operating through these data. There's a strong relationship of the occasions over time. So this is going to be, most of the variability in response time is going to have to do with person differences. I know that based on just looking at this covariance matrix. So this model, in terms of the variance parameters, took 21 of them. So that's the 6 variances plus the 15 covariances. Is that right? Yeah, that sounds right. And then the model for the means has 6 parameters. Here they are. So 6 for the session is the reference. That's why it's zeroed out. And so the expected response time at session 6 is 1672. So that's in milliseconds. So by the end of the study, on average, they take 1672 milliseconds to do this task. And then each of these numbers is the pairwise increment to that ending response time. So session 1, for instance, is higher by 289. And you can put those differences with the intercept and then recreate the means at each occasion. So I have the beta formulas out here by which I made those. And these are the means that we looked at in the trajectory, which we decided was not quite linear, kind of non-linear-ish. All right, so I have a few questions for you with the audience participation portion of the program. By what other name do you know this total answer key model when it is estimated using least squares? So how else would you have learned this model?
Between groups and all?
Not quite, because there's no groups yet, but you're on the right track. It's another Anova.
Repeated measures Anova?
Yes, it is. Which kind?
Unstructured.
It is unstructured, but that's not the word they use. It starts with an M.
Multivariate.
There you go. This is MANOVA, folks. That's what people would call this in a least squares setting. This is a multivariate repeated measures analysis of variance, or that people say it's the multivariate approach to repeated measures, but it is a MANOVA model if you're using least squares. And by what other name do you know this same model if it is estimated in structural equation modeling land?
Is this H1?
This is the H1. Very good. Yes, indeed. It is the H1 model. So this idea of like the most complex, the best fitting that you can have, like this is operationalized in a lot of different ways. And so I want to make the point that we're changing the terminology a little bit because that's what's customary in this field, but it's directly analogous. Yeah. So the saturated model, the H1 model in SEM, that's what this is. In SEM terms, saturated refers to the whole thing, but the word unstructured is analogous to saturated. You can think of them as synonyms, but they're used for each side of the model differently here. Very good. So this is used to give us a baseline to compare against. Our entire goal is to try to get as close to this in terms of the means, variances, and covariances, but use fewer parameters to do so. And more specifically, the fixed effects are going to recreate the saturated means, whereas the random effect variances and covariances, along with the residual variances and covariances, are going to recreate the variance-covariance matrix that's unstructured. Okay, how are we doing? Question. Yes, sir, Carl.
So question about the question you have above these two. What does this F test tell us?
Skip that
I'm
one.
assuming
Thank you.
Yeah, so I'm assuming that just means sessions 1 through 5, all the means, the fixed effects, those all significantly differ from session 6, the reference group?
Not quite. So close though. The solution for fixed effects is phrased in terms of the 5 contrasts of each other occasion relative to 6 as the reference. The Omnibus F Test, as it is called down here, is essentially asking if there are any differences among the 6 session means. So it is a joint hypothesis test of these 5 individual slopes put together. That's what F is telling us is their joint significance of those 5. But the F answer would be the same regardless of which occasion we designated as the reference. So yes, thanks. I skipped the little box here. The F test tells us that the means are different over time. Different how? We don't know yet. That's for us to figure out. Okay, does that help? Thumbs up, excellent. Should I try to start my video again? I'm gonna try it and see if it gets bad. Let me know if I start getting frozen and I'll shut it down again. All right. Any other questions before we move on? Okay, I will take that as a no, but if you change your mind, please be sure and let me know. So then starting from the opposite end of the fit spectrum instead, starting from the worst model and building up. The rationale is that the perfect best answer key model is not always going to be possible. It's only possible for sufficiently balanced data when you have enough cases relative to the number of occasions. If you have unbalanced data or a smaller sample, you can always build up from a simple model though. And so this baseline empty means random intercept model you can always do. It's useful for descriptive purposes as well to generate an intra-class correlation. So you've seen this before. This model has 3 parameters in it. It will have a fixed intercept, it will have a random intercept variance, and it will have a residual variance at level 1. So we're introducing the G matrix again. So we now have a random intercept. The R matrix is type equals VC, meaning diagonal, meaning constant variance assumed on the diagonal with no covariances of the E residuals. So we have, let's see here. Yeah, independent is the structure for the residuals in Stata. And in R, I'm switching back to Elmer rather than the NLME functions because Elmer gets the degrees of freedom right consistently, whereas the LME and GLS functions do not necessarily. And in most of the models that I'm going to show you, we're not going to invoke anything in the R matrix other than diagonal, and Elmer works just fine for that. When I do switch back to trying to see if the residuals need something else, then we will have to switch back to NLME to do that. So the random effect portion then in parentheses here within the formula for R allows us to have a random intercept here for that one. The fixed intercept is the first one. So then in terms of the output, we have our R matrix shown here where the diagonal is the level 1 residual variance. We have our G matrix, which is the level 2, and it has only one thing in it, the random intercept variance. Those two numbers, if you add them together, then form the diagonal of the V marginal matrix. So U at level 2 plus E at level 1, those variances combine to make this 245, 783 number, which is constant over the diagonal. And the covariance that is implied by that random intercept variance at level 2 translates into a constant correlation. So 82% of these data are between or within. Do these as multiple choice questions. 82% is the interclass correlation. Between or within, folks? Couple votes. Yeah, this is between. 82% is level 2 or level 1?
Level 2.
2, yeah. 82% is because some people are better at this than others. That's what I know. Is this pattern likely to be sufficient to describe our data? Absolutely not. This is just a jumping off point, sort of a descriptive statistic. We know that it's not going to hold exactly, but it's a useful thing just to get a benchmark as to what is the relative amount of information that is being contributed cross-sectionally, because of person mean differences is 82%, and the remaining 18% is because of some kind of change or some kind of variation over time. We don't yet know which it is, or to what extent there's both. Right. So then we have a likelihood ratio test that shows up in the output directly in SAS and in Stata, and I added that to the R code, I believe. Make sure I did. Yes, I did. That is my Renova. So it's Anova if you're using LME or GLS. It's Runova if you're using Elmer. And this gives you the likelihood ratio test for removing the random intercept variance. Functionally, what it's telling you is whether the interclass correlation is significantly greater than 0. So with a chi-square of like 691, yeah, it is. So no surprises there. So then the first model that I want to try, well, let's just start with linear, and then we'll see what else this is needed. So this is a review of what we did in example 5. So I'm adding time to the level 1 equation here, and I'm adding beta 1I as the placeholder for how each person is going to get their own time slope. And in level 2, the way that I've written this here is not just the equations, but I have a word that says what the equation is predicting. This is not something that I see often when people write out equations, but it's something that I started doing because I find it really useful. Like, what is this equation for? This is the equation for the intercept. Okay, this is the equation for the effect of linear time. Especially when you get really complicated models that have a ton of level 2 equations or even level 3 equations, I think just a label that says what is being predicted can help people follow if they're less familiar with this notation system. So right now, the individual time slope is composed of only the fixed effect. So what kind of individual differences in change does this model allow, given that we only have a fixed effect? Constant, yeah, no individual differences. This is a parallel change model to start with. Yes, exactly, parallel constant change. So we're just working on the average trajectory right now. We're changing the trajectory from flat to not flat. So time then is the predictor variable that's going into the model as a fixed effect, meaning I want a linear slope for that time variable as a predictor. And I am also saving pieces of output to compute pseudo R square for the change in the residual variance that results from introducing time as a fixed effect, as well as the information criteria, in anticipation of using this model as a baseline for a likelihood ratio test. I am also asking for predicted outcomes according to the model at each occasion. That's how you can generate a line. Essentially, these are the dots that would make the line so that you can show what the model is saying. I have a little macro program in SAS that I wrote called Pseudo R Square that takes as input the number of parameters in the model for the variance, the model that you want to compare against that has fewer parameters, which is the empty model, and the model to be compared of the effect you want the R square for, which is the linear model. So what this is going to do is stack together the variance components from those two models and compute the proportion change in each of them. I also have Excel spreadsheets in the download folder that do the same thing. And if you are a good programmer in R, you can probably figure out how to write a function that does this as well. Let's see, in Stata, same deal. C.time is what's going into the model as a fixed effect here. It is not yet a random effect after person ID. And I'm using lincoms to generate the predictions. You could also have used margins, but I'm trying to keep the code as similar across the packages as possible. And here is the R code that goes with it. Time is showing up here in the first part of the formula. Otherwise, it looks the same. And the analog, when you're using Elmer to do estimate type statements, GLHT didn't work for me, I think, when I tried it, and so I went looking for something else, and Contest 1D is what I found. That is within the Elmer test package. So all the packages that I used in these examples are at the top of the syntax file in R, of course. This one allows you to ask for linear combinations of the fixed effects. So then in parentheses, what the column of ones here refers to is that each of these is built using, at a minimum, the fixed intercept to be estimated by the model. And then adding to it, these blue values are the multipliers of time. So at the first occasion, time is 0. At the second occasion, time is 1, and so forth. And so the pattern of the values here matches what it is in the other programs as well. It's just less explicit that that's what's happening. So this is, I think other people might call that a contrast matrix, but these are the values that multiply the fixed effects in the order in which the fixed effects are going to appear. So we have to know which is first. It's always the intercept. So then we have our matrix output. This is smaller than before, which is not a coincidence, because if we are adding a fixed effect of linear time, we should have explained the time level residual variance at level 1 to some extent. So there's less of that. The intercept variance, I think, went up a little bit, maybe. In this case, that's also an expected consequence of having explained level 1 residual variance. So yep, the conditional intraclass correlation is a little bit higher. So after controlling for linear time, 85% of the total variation is because some people are just faster than others. We have our fixed effects right here, and I'm not going to forget the box this time. So we have our new fixed effect. The intercept used to be 1770, and now the intercept is about 1900. Why did the fixed intercept change so much relative to the empty model? So previously the intercept was 1770, now it's 1900. Why did it change so much? Any guesses? Centered on the first occasion. Ding, ding, ding. That's exactly right. The intercept before was the mean. Conditional on time 0? Also correct. Yes. Now it is the model predicted mean when time equals 0. So the intercept is always the expected outcome when x's are 0. Time is x. This is the predicted outcome at time 0, which is the first occasion. So it's not the exact mean at time 0. It's what the end of the line says it should be. So then we have our fixed slope. Slope estimate is minus, so we'll call that minus 52. So on average, people are getting faster by 52 milliseconds a session, according to this model. And my question over here in the box, is this fixed linear time slope significant, and how do we know? Yes, p-values. Yeah, not a coincidence that the box is right next to the answer. So this is just a reminder that if we're talking about fixed effects, you can stare at the p-value that shows up right next to it. That is fine. So this estimate divided by this standard error forms the t-value that, when combined with our estimated denominator degrees of freedom, renders a p-value. So this is the column that is the tricky part with respect to the NLME package. It doesn't always get it right. And note the difference in these two parameters as well. The intercept degrees of freedom are much lower because it's being treated as a level 2 variable, because the intercept is random across people. So the intercept is like the mean of the person intercepts. And time right now is only a fixed effect. And so it's the slope of the pooled variable without denoting who is who. And that's why the degrees of freedom are so high. So either way, we can stare at this p-value and call it good. Here are the other estimates that I then asked for. So these are the model predicted means from that linear trajectory. So each of these values will be different by about minus 52. And we already answered these questions. The kind of average change this model predicts, linear. All I have in here is a linear effective time. So I'm predicting a constant rate of change that never stops. And because I have only a fixed linear effective time and not the corresponding random effect yet, I'm predicting parallel change across people. In terms of effect size for the slope, there are a number of things that you can do. One easy thing that you can always do with these models is take this t-value and turn it into either a d or an r. So the same formulas that you learned in linear regression for computing effect sizes out of test statistics, you can do that here. If you want to talk about variance explained, that's where pseudo R Square would come in handy. So relative to the empty model, the residual variance at level 1 went down by about 21%. So 21% of what was within person fluctuation over time is because of an average change, and we have then 80% of the fluctuation left to be explained. But remember the caveat with these things. Now, would it be correct if I just said, R square for my model is like 21%? Is that cool or not cool? Yeah, not cool. Not cool at all. How do I make it cool? Or at least as cool as I'm capable of. How do I fix my sentence that 21% of the model's variance was explained by time? Yeah, I clarify. It's not the model's variance or the outcomes variance, it's level 1 variance specifically. So according to the empty model, 18% was at level 1. So what I have here is 21% of the 18%, which boils down to like, 4% or whatever overall, which is not nearly as impressive. Okay, how are we doing? Thumbs up and quick responses, which means that I am not frozen, I think. Unless you're all on an algorithm to just, have your computer manually pop up thumbs every now and again. I had heard stories about very smart children during the pandemic that somehow created programs that would automatically log them into their Zoom class even if they were still sleeping. I thought, that's the kind of wisdom this world needs. So maybe they figured out how to automatically show thumbs. Who knows? Anywho, so one more here while we got a few minutes left. We can make this work. Random linear time. So the addition to this model relative to the previous one that was fixed linear time only, what's new in my equation? There's one new thing in here relative to the previous model. What is it? One vote for U1I. Yes, indeed. There it is. So now the level 2 equations are similar in structure. They each have a fixed effect, followed by a random effect. So we have transitioned from a model that says everybody changes linearly and everybody changes the same into everybody changes linearly, but the extent to which differs across people. So some people can improve at a faster rate than others, but it's still a linear rate that we're talking about. So then time shows up in two different places in the model. It's on the model line in SAS as a fixed effect, and it's on the random line in SAS as a random effect. So that's not redundant. It does go into both places. Those of you who are working in SAS, I just want to make this point. Time and session are not interchangeable. Session is being used as a level 1 ID variable, and it is being used in the repeated line here to organize the R matrix, and that's why it's on the class statement. Time is being treated as a continuous predictor to be given a slope. So if you mess up, if you confuse these two, like if you put session in the random line, your model will break. Because then what you're asking it to do is to allow each pairwise difference relative to that reference mean to differ across people. And that's actually not identified. You can't do that. So time is the continuous predictor that goes on the random line. Likewise, in the Stata world, I got C dot time as a fixed effect, and then time shows up after the colon in the random effect. Intercept is always there as a default. And that means I had to add covariance unstructured to the Stata code to allow it to estimate the covariance between the intercept and the linear time slope. That also had to happen via type equals UN on the random line in SAS. And then R folks, your time predictor shows up in two spots as well. In the first part of the formula as a fixed effect, and then inside the parentheses as a random effect. And I have the 1 here to remind myself that the intercept is also random in this model. And I'm asking it then to do Anova likelihood ratio test to compare against the fixed slope model to see if our random slope helps. So that same thing is happening via LR test in Stata, and I wrote my fit test macro to do so in SAS. All right, survey says, so our matrix relative to the previous model has shrunk a little bit, but I'm not going to say that the variance has been explained. What should I say instead? So there's less variance at level 1 after adding a random slope, but I'm not going to say it's been explained. Yeah, I could say partitioned. Any other synonyms you can think of? I can think of a few more. I like partitioned. Attributed, I like that one too.
Decomposed.
Decomposed, I like that one. Although I've been told that's a bit morbid. The only other time you hear decomposed is like relative to bodies in the ground or something. But that's the one I used to say most frequently. I like decomposed. Partitioned, attributed, split, rearranged, reallocated. Those are the words that I would use. Because what this model is saying is that part of what we thought was just E fluctuation around the individual lines is actually because each person needs a different line. And once we give each person a different line, that makes the E's smaller as a result. But we still don't know why each person needs a different line, which is why I don't want to use the word explained. We've just reallocated, decomposed, partitioned what we called level 1 error variance into a level 2 random slope variance instead. Good. And here it is. So here's our G matrix. The intercept variance is 253, 258, and the slope variance is 2233. So the intercept variance in this model is a different number than it used to be. Why do you think that change happened? Why would the intercept variance be different after adding a random slope variance to go with it?
because the random slope depends on the random intercept?
Uh,
Is that part of it?
I'd say it the other way, but you're definitely in the right ballpark.
Okay.
Yeah, the intercept depends on the slope, meaning it's conditional. So yep, in the same way that the fixed intercept became at time 0 once we added time, the random intercept becomes at time 0 once we add time to the random part of the model. So it's a parallel exact process, but it's happening on the two sides separately. So yes, this number in the random intercept spot here is specifically intercept differences at time 0. If you changed where time 0 was, would that number change?
The intercept would, but the slope wouldn't.
That's right. The slope would stay the same, but the intercept would. Because the spread of the y-axis, if people change differently, is going to depend on where you are on the x-axis. Where you are in time dictates how far apart people are from each other. But their slopes stay the same in this model because the slope is the highest term, it's unconditional. The intercepts and slopes are correlated negative 0.53, and the way that I would interpret that is also specific at time 0. So where you start in this study is correlated negatively with your rate of change. So people who start out the highest change the most, I think is what that becomes, because this is a difference in decline. And that makes sense because if you're not good at this, then you have the most room to improve. So it's kind of a consequence of the process. So the addition of this new random linear time slope variance and the covariance that goes with it, then the combination of those three things plus the R matrix residual variance, that builds our combined V. And so V now has a pattern to it that says that the total variance changes quadratically over time. And here's the formula for where those numbers came from. The variance at a given occasion is intercept variance plus a function of the slope variance multiplied by time squared plus 2 times the variance at which occasion it is times the covariance plus residual. And the covariance between any two occasions is a function of intercept variance at a minimum plus the other model parameters multiplied by which two occasions those are. So this is a fairly complex function, but this is where this matrix came from. That's how it got built. And then here's the correlation version of it once you standardize to have variances of 1 on the diagonal. Okay. So how do we know then if we should keep this thing? How do we know if adding a random linear time slope variance helped? Yeah, we're in REML. So likelihood ratio test. Yep, go ahead.
So, and we can use the likelihood ratio test because it has the same, we're not changing the fixed effects, we're just worrying about the other side.
Exactly. Yep, we kept the fixed effects constant as is needed because we're using REML, but also as makes sense because what we want to know is the individual differences part specifically. So holding the constant change part equal across models then allows us to isolate that new term and its covariance with the intercept. By the way, this is the p-value that you should not use. So here are the variance parameters in the model, and it prints a z-value and a p-value. Ignore these. These are the ones that are treating the variances as having a two-sided normal sampling distribution, and that will be less and less true the closer the variance estimate is to 0. So ignore these p-values. We're going to look at the likelihood ratio test. All right, so survey says, here it is. Yes, sir.
Yeah, I have a quick question. In one of these slides, you mentioned that random effects can be significant. In that case, you mean that we can see if these random effects are significant or not using likelihood ratio test, right? Not something like p-values for random effects?
Yeah, so it's not, the p-value that I'm saying not to use is this one specifically. That is the Wald test that goes with the variance number. These are the ones that are not going to work very well. So yes, we use the p-value that comes out of a model comparison likelihood ratio test instead.
Great. Thank you.
Yep.
Lisa, can I want to ask a question too, and I'm
Yeah.
hoping this isn't just, I'm trying to make sure this is a valid question, but why not just use AIC or BIC to compare model improvements for everything so that we don't have to worry if, likelihood ratio tests are appropriate or not?
Because AIC and BIC as their primary ingredient is -2 log likelihood.
Okay. So those are going to be off. You wouldn't be able to do that in REML.
Nope.
Okay.
Nope.
That makes more sense.
Yep. They are used, I think, as supplemental information to the likelihood ratio test, and they're also used in the case of non-nested models, which are somewhat rare in this world. But yeah, they're tied to likelihood too, so they have the same limitations. So survey said we have change in the chi-square, or excuse me, change in the -2 log likelihood creates a chi-square, the test statistic of 42, 2 degrees of freedom, and a significant p-value to 10 digits here. And one last question and I'll let you go. Reviewer 3 wants to know why I didn't use a mixture chi-square on this. How do I answer?
Can these go negative?
No.
No.
Mm-mm. What does a mixture chi-square change?
The cutoff.
The cutoff. So the cutoff for p less than 0.05, if I ignore this problem, is 5.99, and the cutoff, if I do it properly via a mixture, is 5.17. I'm at 42. Am I going to come up with a different answer if I do it the right way?
Reviewer 3 seems to think so.
Yeah. No, my p-value is 0 to 10 decimal places, right? Like, I am not going to come up with a different answer. So, if you pass the cutoff by the more conservative standard, then the mixture would also be significant. So, yes, nope is indeed the answer. All right. Thank you, folks. I will stick around here in between classes if anyone wants to ask questions. Otherwise, I will see you next week, and I will let you know where we will be. So thanks for being here. Have a good weekend.